Good.
We're good. We should be proud of ourselves.
Okay, let's start with this.
Whoa, what is that?
Everybody, attention up here. Okay, so 14:1. Chapter 14 is all about regular polygons. So the first thing we have to actually figure out is what a regular polygon is. And we're going to talk about some things that go with the circle that goes around the polygon. Okay, that is circumscribed around the polygon. Okay, first of all, what does a polygon mean?
Doesn't it just mean a multi-sided shape?
Yes.
It's more than four?
No.
Not even
Well,
necessarily.
Oh.
all of them, it's a
Shape.
shape that has straight sides and it's closed. Okay, so it's a closed shape. Okay, a regular polygon. I will give you an example. An equilateral triangle is a regular polygon. A square is a regular polygon. What do you think a regular polygon, based on those two examples, what would you say is true about those? Yeah.
Symmetry?
They have symmetry, that's correct.
Maybe their sides are supposed to be equal.
Yes, regular polygons have sides that are equal. They do have symmetry because of that. Okay. What else is true about an equilateral triangle and a square besides their sides equal? Yes.
It's equal angles.
Yes, the angles are equal. So when we're looking at regular polygons, the equilateral triangle is one, because all the sides are the same and all the angles are the same. A square
Struggle week.
is one.
It's empty.
Okay, guys, let's pay attention to what's up here. The square is one. I cannot draw a pentagon at all, but that's one where all sides are the same and all the angles are the same. I'm a little bit better drawing an octagon, or a what is this called? Hexagon. Hexagon. Okay. So again, all the sides are the same and all the angles are equal. Okay. So that's what's a regular, and you can go on up to 10, 20, 30 sides, and all those angles would be equal. Okay. So that's one of the things that we're looking at. It's the regular polygon. Okay, because this whole chapter is about regular polygons. Okay. And what you can do with regular, and if you look on page 573, it shows you the pentagon, the hexagon, the heptagon, which is 7, octagon, nonagon, and decagon. Decagon is 10, just like decade is 10. I can't tell you where hepta comes from, but it must mean 7 in some language. Okay. Dodecagon, if you hear the word dodecagon, that's 12 sides. Dodecagon has 12 sides. Okay. So, when we have a regular polygon, any regular polygon can be inscribed into a circle. So if you have an equilateral triangle, it can be inscribed into a circle. All the vertices, the circle hits all the vertices. Okay, so here the circle is circumscribing the triangle, the equilateral and the triangle, just to review the words, is inscribed into the circle. Question for you. What is that point right there in the center called?
Circumcenter.
Circumcenter, it's called the circumcenter. Okay, that is called the circumcenter because it's the center of the circle that goes around that. The circumcenter, which is kind of interesting, or the circle, has a radius, the distance, whoops, that was crooked. The distance from the center out to there, out to the edges of the, so that's its radius. This length is its radius. Okay. So those are some things that we can look at. Okay. So central angles, you can see that the central angles, there's 3 equal central angles here because you have this one, and this one. So all the central angles are equal. So the central angles inside the circle are equal. And that's true no matter how many sides you have. It's true for squares, it's true for regular pentagons, it's true for regular hexagons, etc. Okay? How can you find, just thinking about this right now, how would you find the measure of the arc around this or the measure of the central circle if you have a triangle? How many central angles will you have? 3. Because it goes out to each vertice, right? And there's 3 vertexes.
Is this an equilateral triangle?
That's the only one that we can
Oh,
have,
okay,
remember? So yes, they are all equal. So how can I find out what the central angle is?
They're all double the central angle.
They're all no. They're
One of the things.
well. It's not an inscribed angle.
Oh, 360.
They're all 120.
It is. It's 360 degrees divided by n. Get used
That's
to,
on the inside.
okay guys, get used to us using n. It's the number of sides. So we're going to use this quite frequently, but the central angle is equal to this. 360 divided, so in this case, 120 degrees for a triangle, okay? If I had a pentagon inscribed in, I have a pentagon.
I need to put the pencil down. Put it down.
Put it back in his misery.
Okay, what is the size of the central angle if I have a pentagon inscribed in a circle? What is the size of the central angle?
It's 72.
Okay, so it is 360 degrees divided by the number of sides, which is 5. That is 72 degrees. So you can always find your central angles in any regular polygon that's inscribed into a circle. You can find those central angles. Okay, it's very, very easy to find those. Okay, there is one more thing that they talk about. I'm going to redraw another picture because it's a little harder to see. And it's a special word that I just tell you I don't use very often, so I couldn't even remember this one. But let's say you have your equilateral triangle. Okay. This line that's drawn from okay, so if you have some sort of regular polygon that's inscribed, okay, if you go from the center of the circle, okay, to the opposite side at a 90-degree, this is called, I call it the perpendicular bisector because that's really what it is, but they gave it a special name and it's called the opossum. Opossum.
So it's opossum if you have opus.
Yes, it's an opossum. Okay,
The opossum?
it's opossum.
Wow.
That is basically the perpendicular bisector from the center of the circle. Oh, the perpendicular bisector of a side to the center of the circle. Okay, crazy name, opossum. Okay, like I said, I don't hardly ever use that word. I haven't even heard it used a lot. Inscribed, circumscribed, those things are used, but this is not used that much. Okay. That's really all that 14.1 is about. Okay. So we're going to go into 14.2. We are really just defining things, talking about the central angles, talking about what the opossum is called, but that's really all we're talking about. It's just describing what the situation looks like. So 14.2 is going to go into how do we determine the perimeter of one of these polygons. Okay. 14.2 is finding the perimeter of a regular polygon. Okay, we're going to use, we'll try to use I'm drawing a really beautiful one, right? There's a hexagon. Kind of regular, kind of not. We're going to mark it so that it is regular, okay? Just because that makes it easier, okay? So the perimeter okay, so basically it goes through a theorem here, and I'll show you what it's trying to show you. But basically, this is what you have. If you know this distance right here, right? The perimeter is really going to be the number of sides times the length of one. Makes sense, right? But we don't necessarily know that, okay? So what we're going to use is the fact that we have this, and we can come down here, make an opossum, which is really a perpendicular bisector, okay? if we know the radius, okay, we're going to look at, that is not 100. Oh. Can somebody tell me what the size of that angle would be?
So it'd be, because the top one's 70, no, half of 72, so it'd be,
Wait, we did that for a
36.
pentagon.
oh, my bad.
I know.
Yeah, you're
Yeah.
gonna have to find it.
So it would be 30, right?
Yes, because you have 360 divided by 6, which is 60, but this is half of that, so 60 divided by 2 is 30, okay? They use the formula like this. What it comes out to be, because we have to divide by this, so if I change, instead of dividing by 6, I take 360 divided by 12, twice it, that will also give me 30. So one of the formulas is basically, you can either do it one of two ways, okay? It's 360 times 2n, so this is the formula. So your angle up here, right there, is going to be the angle, well, it's actually half of the angle, half of the central angle. You can find by this, 360 divided by 2n, or if you want to do it this way, I could do it 180 divided by n, because look at 360 divided by 2 is really 180. Okay, so if this makes more sense to you, because you can say, oh, I know there's 360, there's n of them, but we have to divide that in half because there's 2n really. Well, that reduces down to 180 over n. So 180 over n is going to be that angle right there. Okay, so if I can find that, then what we know is the radius is this amount. We know that this is going to be s over 2. Do you guys agree with that? This section right here is s over 2. The side length over 2. Okay, so what we can set up is from this angle, we have this side over this side, right? Which is the sine, because it's the opposite over the hypotenuse. So from angle in the center, it's going to be the opposite over the hypotenuse. Okay, our angle in the center we just found is going to be 180 over n. So this is going to be the sine of 180 over n, inverse sine, is going to equal the s over 2 times the radius. Okay. Why do we come with s's in?
It's really satisfying though.
Oh, but what we know about this, the perimeter, is n times s, correct? Okay, well, we're going to solve this for s. What this becomes when we solve it for s is it becomes 2 times r times the inverse sine of 180 over n equals s. You guys agree with that? Alls I did was divide or multiply both sides by 2r. I also know that S is the same as P divided by N, so I'm gonna say this. P divided by N, okay, because if I look at this, P divided by N is the same as S, so I'm just substituting that in. Okay. So what we then come up with is 2NR sine -1 of 180 over N equals the perimeter. Do you notice the only length we need to know is R? We only need to know the length of R. Because this deals with the number of sides, that deals with the number of sides. So this we can all find, we just need to know what the radius is and we can find the perimeter. Okay. Now they write it a little bit different. What you will see in the book is this, because they give a special name to some of this. You will see that it's 2N, capital N, R. That equals the perimeter of your polygon, or of your, regular polygon. And because all of this can be found just by the number of sides, this is called N. So it's because of the number of sides. What we put in there is N times sine -1 of 180 over N. So we can find N just based on the number of sides. So they have you find that, you plug that in, you multiply it by 2, and you times it by the radius. Okay. And that's how you can get the perimeter of any polygon that's inside. Okay, so that's what they're asking you to do. So this big N is all based on how many sides your polygon has. Very easy to find. Number of sides times the inverse sine. That's N. Know what your radius is, multiply it by 2, and you've got the perimeter of the triangle. Or whatever it is, the polygon.
So that's the
Yes.
perimeter, and that is, what is this one?
That's the
Also
same
perimeter,
thing.
but
It's
it's just
also
longer.
perimeter. It's just that they replace in the formula in the book. This is a legitimate formula for perimeter. Okay? What they do though, because they don't want all that stuff in there, is they say capital N, we refer to capital N as being the number of sides times the inverse sine of 180 over N. Yes.
So small n is the number of sides?
Yes, small
What's
n is
capital N?
always, capital N is this,
Okay, it's just that
that
formula.
quantity right there. Capital N, because it's saying this special formula that we use based on the number of sides is this.
And n equals, capital N equals the perimeter all the way around?
No, capital N doesn't equal the perimeter, it equals this. The number of sides times the inverse sine of 180 divided by the number of sides.
Oh, and that gets us
And
the,
that's just, and that
That
gets
gets
us
you the
perimeter.
big N.
and the big N is the length of one side?
No, it's the
The
perimeter.
big N is just part of the perimeter formula.
Oh,
Oh, so you have to do that, and then you
You
plug
do
it,
this first.
and then you plug it into 2N
So yeah,
times
so let's
R.
say that we have a, let's just use this problem right now, okay? Let's say that we have a pentagon, which means N is going to equal 5. Does everybody agree with that? It's a pentagon. All right. The radius of the circle inside is going to be 3. Okay, I'm just giving you the information here. Okay. So the first step we do is this. We find, based on the number of sides, we find out what this value big N is. Okay, so what we get is N is going to be equal to 5 times the inverse sine of 180 divided by 5. Okay, what is 180 divided by 5? More than that.
That's not it.
36. So n will equal 5 times the inverse sine of 36 degrees. Whoops. Okay, somebody take the inverse sine of 36. They should have calculators. Take the inverse
0.5.
sine. What is it?
0.5877.
Okay, so n is going to equal 5 times 0.5, what?
877.
877. So what is n going to be?
2.938.
2.938. Let's round that to 2.94. Okay, so now I found n. So now to find my perimeter, I take 2 times my n, which is 2.94, times my radius, which is 3, and that will be the perimeter of that polygon. So 2.293 times 3, it's a little less than 18, 17 something, is that correct?
Yep, 17.6.
17.6 is the perimeter of the pentagon that has a radius of 3 for its circle that is circumscribing it. Okay, so that's all this formula is showing, is if you have just the radius, you can find the perimeter using this formula instead of going back and looking at all that stuff. And this part is very easy to find because it's all based on how many numbers of sides you have. Okay, it's all based on how many number of sides you have. This one you have to be given. If you're not given this one, it's not going to be easy to find this perimeter. Okay, that's just how that works. Okay, so that's all the notes. We're going to do a few up at the board right now to get us to stop.